In this podcast, we're talking about calorimetry. And calorimetry is a method for determining how much energy is transferred, how much heat is transferred during a reaction or a process. So it is a process for measuring heat based on observing temperature change when something absorbs or loses energy as heat. And we often use what's called coffee cup calorimetry. That's simply because we use this good old styrofoam cup, which is a very good insulator, so it doesn't lose a lot of energy. Not a lot of the heat gets through. And in order to find out the particular energy of a system. Okay. So we look at how much stuff we have, the starting temperature, the ending temperature, and that allows us to figure out how much heat was transferred. Okay. So after we collect all our data, and we're collecting either mass or volume, initial and final temperatures, and be careful of this. Sometimes in a free response question or even a multiple choice in the AP test, it might say what data is needed to be collected in a calorimetry experiment. And if you say delta H or delta T, you would be wrong because you don't collect delta T, you collect initial and final temperatures. Okay, and then we'll use formulas to figure out the energy change. Now, when we use a coffee cup calorimeter, we call this constant pressure calorimetry, and that's because Q and H are going to be the same thing, and that's if you look at this setup right here, if we have a coffee cup and we are measuring what's happening in that coffee cup with a thermometer, that coffee cup is really open to the air. Even if we put a little coffee lid on there, it's not allowed to build up pressure, so the pressure is going to remain pretty constant. And that way, any heat change is all enthalpy change. Okay. So there's a few terms that you need to know. Heat capacity you can find this on a table, and it's heat capacity for different substances, and it's the amount of energy required to raise the temperature of a substance by 1 degree. Okay, and so it's joules per degree C or joules per Kelvin, because 1 Kelvin and 1 C is the same size. Okay. You also will sometimes see specific heat capacity, which has the symbol of C, and it's the same thing as heat capacity, but it's specific to the amount of energy required to raise the temperature of 1 gram 1 degree C. Okay, so specific heat is the quantity of heat transferred divided by grams and temperature change. So the difference between these two are just grams. This has a mass component and this does not. Okay? Sometimes you will see heat capacities listed as molar heat capacities. So you always have to, it won't necessarily tell you this is molar heat capacity or specific heat capacity. It will give you a heat capacity and either tell you joules per mole K or joules per gram K, and you got to look at that, because if it's moles, you got to convert your amount of substance to moles. If it's grams, you got to convert it to grams. Okay. So the formula we typically use when we're talking about energy change, and this could be enthalpy or Q, is this good old Q is MC change in T, where Q is the quantity of heat, M is the mass in grams. In this case, it's grams. It's not like kinetic energy where we use kilograms. And the temperature, final minus initial. And it doesn't matter whether we use degrees C or Kelvin. Okay? And then C is the specific heat capacity, which would be in joules per gram degrees C. Now, one value you do need to know is the specific heat of water in the liquid state is 4.184 joules per gram degrees C. And I don't think that value is on the equation sheet. No, it is not. But you need to know that. And once you've done as many problems as we have in this unit, you'll know that by heart. Okay. Now, this is also known as 1 calorie per gram degree C, because in fact 1 calorie is 4.184 joules. Okay, and calories used to be the standard unit for talking about energy. Now we use the joule. Now, one of the interesting things about water is it has one of the highest specific heats known compared to a lot of other substances. Water specific heat is very, very high, which gives it a lot of unique properties. It takes a lot of heat to raise this 4.18 is a high number. It takes a lot of energy to raise the temperature of water by 1 degree. And the whole key behind calorimetry is that the heat lost by the substance, whatever's going on, whatever's reacting, whatever process change is going on, is going to be equal to the heat gained by the water. And this is based on the law of the first law of thermodynamics, that heat or energy can't be lost or gained. And so we usually do these reactions in water, and because we know the heat capacity of water, and we can easily measure how much water we have and how much the temperature changes, whatever temperature is lost or gained as a result of the reaction, it's going to be lost or gained by water. Okay, so you'll see how easy this is to apply. So let's just talk a little bit about units of energy. So, like I said, used to be we used calorie, and actually we're kind of very ancient in the United States. We use BTUs, but most of the world uses joules. Okay, so calorie is the amount of heat needed to raise the temperature of 1 gram of water, and this should say by 1 degree C. Okay, and a kilocalorie is 1,000 calories, and if you look at your food labels and you say it has, a piece of candy has 200 calories, it really has 200,000 calories, because those values on your list of substances is actually listed in capital C, or kilocalories. Again, we're the only ones that still use calorie, and if you were to look at a Diet Coke label in, let's say in England, it would say low joule soda or beverage as opposed to a low calorie beverage. Okay, so joule is the SI unit. That's pretty much what we're going to use. You'll see a couple problems with calories, and so you need to know 1 calorie is 4.184 joules. Okay, so let's take a look at this problem. We have a coffee cup calorimeter, 100 milliliters of 1 molar sodium hydroxide, 100 milliliters of 1 molar HCl. Both solutions were originally at 24.6 degrees C. After the reaction, the temperature is 31.3 C. This is going to give us my change in temperature. Assuming that all solutions have a density of 1 gram per centimeter cubed, and a specific heat capacity of whatever water's is, and that's 4.184 joules gram C, we want to calculate the enthalpy change for this neutralization reaction, and we want to assume that no heat is lost to the surroundings or the calorimeter. So if we are using a coffee cup calorimeter and we are measuring, kind of a bad thermometer, what's happening to the temperature, the assumption we're going to make is that all of the heat stays contained and none of it leaves the calorimeter. So any heat that is generated as a result of mixing sodium hydroxide and HCl is heat that's going to be absorbed by the water that makes up these solutions. Okay? So we're talking about these solutions being predominantly water, which is why we're using the heat capacity of water here. Now, this density information allows me to, and again, this is the density recognized of water, to take this 100 milliliters and say, well, okay, that's also 100 grams. Okay. So if we think about Q equals MC change in T, we can use this amount of each substance, which together is 200 milliliters, and because the density is 1, that gives me 200 grams. And because I have essentially 200 grams of water in that coffee cup calorimeter, right? I've got 100 milliliters of this, which is about 100 grams of this. I've got 100 milliliters of this, which is about 100 grams of this. So the amount of water that's getting heated up is about 200 grams of water. All right, and it said that we're going to assume that the heat capacity is 4.184 joules per gram degrees C times my change in temperature. My change in temperature is going to be 31.3 minus 24.6. So if I go ahead and I plug in the values here, I'm going to get, my calculator will say 5606 joules. Okay. This is a degree C, so this C and this gram cancels. I'm left with joules. And looks like I want, let me see, 2 sig figs, so I'm going to go with 5.6, and I can make that kilojoules. And I got to think about what's happening here. This is going up in temperature, which means that I have an exothermic reaction. This acid and base, when they neutralize, generates heat, which is absorbed by the water. So this has to be negative. So it's going to be negative that many kilojoules per moles of reaction. Remember, this is how the College Board wants us to do this now, is we want to use per moles of reaction. Alright, so when 1 mole of methane is burned at constant pressure, 800 kilojoules per mole of energy is released at heat. We want to calculate the change in enthalpy for a process in which 5.8 grams of the sample of methane is burned at constant pressure. So this is not really a calorimetry problem. This is back to being a stoic problem. Okay, so let's write the equation. Make sure we, so I have methane plus oxygen giving me CO2 plus H2O. So regardless of what the stoic is here, what I know is 1 mole of methane is going to produce 890 kilojoules per mole of heat. So that's going to be, my delta H is negative 890 kilojoules per mole. Okay? So we want to calculate delta H for the process in which we only have 5.8 grams sample. So I know my answer has to be negative. This is an exothermic reaction. So I'm just going to do some stoic. I have 5.8 grams of methane, and the molar mass of methane is 16.05 grams, is 1 mole of methane. And 1 mole of methane, looks like right here, is 890 kilojoules. And so this is going to give me, if I plug this in my calculator, I get 320 kilojoules. But it's going to be negative, right? Per mole of reaction. Alright. Constant pressure calorimetry. Alright. When I have 1 liter of 1 molar barium nitrate and solution at 25 degrees mixed with, Alright, mixed with 1 liter of 1 molar sodium sulfate in a calorimeter, a white solid forms, barium sulfate. Temperature of the mixture goes from 25 to 28.1. Assuming the calorimeter absorbs only a negligible quantity of heat, in other words, it's a good insulator, I'm not losing heat through the calorimeter, and the specific heat capacity of the solution is 4.18 joules per gram degrees C, and that the density of the final solution is 1 grams per milliliter. And I want to calculate the enthalpy change per mole of barium sulfate formed. Okay, so we got to start off with the balanced equation, right? I'm going to write it up here. So I have sodium sulfate plus barium nitrate, and I'm going to get barium sulfate, my solid, plus sodium nitrate. Okay, so I end up with, for one of each of these, I end up with 1 barium sulfate. Okay, so what I want to do is, I can do my Q equals MC change in T again, because I got a calorimetry problem. So my mass, I have 1 liter of this and 1 liter of this, and again they're mostly water. 1 liter is 1,000 milliliters, and based on the density, which we say is 1 gram per milliliter, that's 1,000 grams. This is 1,000 grams, so I have 2,000 grams. Whoops. Times my heat capacity, 4.18 joules per gram degrees C, and my change in temperature, I went from 28.1 degrees C from 25 degrees C. Now, again, I'm going up in temperature, so I know right now I'm going to have a negative enthalpy. Alright. So if I multiply 2,000 grams times 4.18 joules, my grams cancel, my C cancel, I'll get my change in temperature here. And when I plug that into my calculator, I get 25,941. Okay, so my units are joules. Looks like I want, let me see, 3 sig figs. So it's going to be 25.9 kilojoules per mole of reaction. To the negative, though, it's exothermic. Okay. Alright, so you're going to do quest problems and some problems in the book.